Now, given the scale of this operation and the speed at which we need to do this, how do I actually do this? What is the thing that I need to have inside the router, and how do I actually evaluate the performance of some forwarding mechanisms? Whether there are multiple options you can think of. One is I can implement this as a part of the software solution. I write a code and then I execute that, and every time you receive a packet, and then that code actually goes and searches inside the table whether some entries are matching. And the second thing is I can implement this in the hardware and give this routing table to that hardware, and then that will do the comparison and give you what is the best route or the port number on which you need to forward this. And the third option that you have got is something called as the ASIC, or application specific integrated circuit. So, one option is you implement using some data structure, you implement is in the software code, or the second option is you can use the hardware, something like FPGA or other component, or third option is you build something called as the ASIC. ASIC stands for application specific integrated circuit. What it means is this hardware is customly built for only doing that lookup operation, forwarding decisions, nothing else. This is not a generic purpose hardware, meaning that you can compare that our computers are generic purpose processors. You can do a lot of things on that. I can run in word processor application, I can do might be in video play, I can do something else, I can write a C program and execute. All of this is running on the same processor. But this ASIC is not something like that. This is, if it is designed for one purpose, then only for that purpose it can be used. If it is meant for doing the lookup operation in the routers, only for that you can actually use this ASIC. So, those are the options that I got. Now, which one is better? So, whether ASIC is better, whether the software implementation is better, or I can use the hardware and then do the implementation. So, I need to make an informed choice. So, how do we evaluate the performance of the lookup operation? What are the metrics that are available, whether the software implementation is good enough for me or it's not enough? So, one obvious the metric that we want to use is something called as the lookup speed. How much time it takes to do the search operation, do the string matching. So, larger the time it takes, not good it is. So, lesser the time it takes to do these operation, better it is. That is one obvious metric that we want to use. And the second thing is how much amount of the memory or the storage that routing table itself takes. So, if it is taking too much time, too much space, then probably that is not the enough. So, if I have to store the entire 32-bit type address in the routing table, then that is going to be actually a lot of and other than this, the data structure that you are going to implement will also consume some amount of the memory. So, once I represent the routing table in the form of some structure, how big that is going to be, whether it is going to be very optimized or it is going to take lot of memory, is another metric that is going to govern. And the third thing is, as I said, as the new people join the network, there will be new entries that are supposed to be created inside the routing table. It requires that update operation. So, what it means is, if I structure the routing table using some data structure, let us say for hypothetically data structure X, and what it means is, when a new routing entry is coming, I want to add this, it means that I need to modify that X, data structure X, to accommodate that new entry. So, what is that it takes to do the lead time? Do I need to completely change X and rewrite from the scratch? A large number of the changes are required, or let us say I represent in the form of the linked list, and every entry in this one is telling about this is the prefix number 1, this is the prefix number 2, and so forth. Let us say I have got n number of such prefixes, and I want to add n+1 prefix. So this might be just adding a link from the Pn to Pn+1. This probably does not require much of addition. But on the other hand, think of this case, all of these are actually are in the sorted order, and you are going from the one sequence P1 to P2 and P3 up to Pn. And if a new entry is n+1 is fitting, let us say after the 100th entry, then you need to traverse all of them, insert that node at the 101 position, push the 101 existing 101th node and to the right, and then do work. This is end up work. So if I come up with some data structure to implement or represent this routing table, and new entries are going to come, or existing entries might need to be deleted. So in that case, how much of the effort that it takes to do that update operation or the deletion or the addition of an entry in the routing table. So that is another performance metric. So something which is taking less amount of effort and the time to do the update operation is the better one for us. And fourth metric is obviously the scalability. We are talking about the routing tables which are going to keep the entries for the entire internet, for the routers, typically for the routers which are running in the backbone of the internet service provider networks. So obviously new people will going to join, new prefixes will be coming, and you need to have the scalable implementation. So meaning that the data structure that you come up with should be able to handle large amount of the prefixes. And the fifth metric that one uses something called as the implemented flexibility. So can I make the changes quite quickly? If I want to migrate from one to another one, can I do that? If the data structure is able to give you that flexibility, then better it is. So in nutshell, I got a bunch of options. So lookup operation need to happen quickly, and I have got an option to implement that lookup operation as a part of the software code, or I can build custom hardware, or I can use something called as the ASIC. So in the beginning, obviously when the network started, people started implementing the routing table in the software, and then when software implementation would be obviously slower than the hardware, and then slowly people migrated to the hardware, and we do have a mixture of the software implementation and also the hardware implementation. So we will see the exact data structure, some of the data structures used for the software implementation if I have to do that, and then if I have to do the search operation or the routing table for inside the hardware, how do you exactly do that, both the things inside the course. So let us take a look at the software based implementations, how they exactly look like, what kind of the data structures can I use to accommodate or store this routing table. So what I am going to do is I am going to have a bunch of prefixes. So let us call that prefixes with the notation P. P1 is one prefix, maybe I can do the star, anything, any irrespective of any IP address that you have got. So you forward it to port number 10, that is the prefix number, routing table number entry what is saying. And similarly, this is also called as the default route, and most of the routers actually have such default routers. So if you don't find a matching entry, you do the routing by entry. So a routing table is said to be complete when you are able to make a forwarding decision for every incoming packet. Doesn't matter what is the IP destination IP address of that particular packet, it should be still able to do the routing. So if you are not having entries for some of the prefixes inside your routing table, so in order to make the routing table complete, what you do is insert this default routing entry inside your routing table. So that makes it complete. So you have some entries for some prefixes, and the rest of the prefixes for which you don't have the entries, you do the routing by this default. The second one, it prefixes, it might say that it is starting with 0 star. So, any IP address which is starting with 0, doesn't matter what is the rest of the 31 bits are, you need to forward it to port number 1. That's the second prefix saying. And the third one is saying, if your IP address is starting with 1 and doesn't matter what are the rest of the 32 bits are, you forward it to port number 2. Similarly, I have got might be 00 star, this is going to port number 4, and P5 is prefix number 5 is saying if it is 11 star, then you forward it to port number 5, and P6 is saying 110 star. If the starting IP address is 10, then you forward it to port number 2, and the P7 is saying 1111 star, you need to forward it to port number 3. So, this is there are 7 prefixes inside my routing table, and these are the entries. Now, if I have to do an implementation, what is the thing that I can do? So, one of the simplest algorithm that you can think of here is something called as the tree-based structure. Tree, a generic name is something called as a trie. Trie is an n-way, a node can have n different childs. So, you can construct a trie incrementally for these prefixes, meaning that today I have these 7 prefixes. I am going to build a tree or the trie for only these 7 prefixes, and I get a new one which is the 8th prefix. Then I am going to incrementally modify this trie structure to accommodate that 8th prefix. That is what it is. So, how do I actually build this? The simplest form of the trie is called as something called as the binary trie. So, as the name suggests, there are at the max 2 childs for every node. I start with the way I construct the routing table for or the trie for this set of the prefixes. This is, I start with the root node and I could pick up one prefix and then add the nodes to the left of this root node or to the right of the nodes to accommodate what is the corresponding to whatever the prefix is saying. So, every time I have a 0 in the prefix, I take the left path. Every time I have a 1 in the prefix, I go to the right path. So, let us take this for the time being, let us ignore this P1, let us take this P2. What it says is, it is 0 star. So, I am going to add a left child to this root node. This is my P2. And third one, P3 is saying 1 star. I start with the root node and then this is 0, this is 1, and I add a node here, this is my P3. Every time some prefix is matching, what I am going to do is, I am going to highlight that particular node with a color. Maybe this is my P3, indicating this is a prefix is matched, 1 star is matched. So, that is why this is marked, and 0 star is matched here, and that is why this is marked. Similarly, star is there, you do not have to read any IP address able to match, that is identified by marking the root node itself. So, anything does not matter what is the IP address, so you should match that, and I continue doing this. So, I take the other prefixes and then add the entries to that. So, for example, the 4th prefix is saying 00 star, and I already have one prefix which is 0, and we have come to the node P2. To accommodate one node 0 I require, so I am going to have a left node with the 0 to this one. So, this is my P4, and P5 is saying 1 followed by 1. So, I am going to add a right child to this node, this is my P5, and P6 is saying 110 star. So, 1 is already there, I read 0 and come to the left, this is my P6, and P7 is saying 1 1 1 1 4 times, 2 times already I've crossed here this one. So another one come here and then another one go to the right. So again I'm going to mark these nodes with the appropriate things. So this is, or this is P5, P6, and then this is my P7. So remember that this node is actually not marked. So wherever the prefix is matched, that node is actually marked. So this is how the binary trie is actually constructed. So for the entire set of the prefixes that you have in the routing table, you have only one such kind of the tree. Here the prefixes are having up to 4 bits. So ideal it might have the 32 bits. So as the number of the bits in the prefixes increases, the height of the tree would also correspondingly increase. So for example, if I have a new entry which is saying something like this. So let's say P8 is saying that this is 0 0 0, 6 times 0. What it means is extending this node by times 0 and end one. 2 zeros I already have read, first one, second one, third one, fourth one, fifth one, and then the sixth one. So and I am going to mark this as the node corresponding to the prefix P8. So you can see this, as the number of the bits prefix length increases, the height of the tree is going to increase. So the prefix can be at max of the 32 bits. So corresponding to that, the binary trie can have a height of the 32. So 32 level is there. So how does the lookup operation, if I have such a trie constructed, and how is the lookup operation done? So let's say I receive a packet with the IP address let's say 11010. Now I need to traverse this trie and then find out what is the best match for this particular IP address. So the first bit is 1. You start with the root node, and then when nothing is matching, by default this P1 is anyway matching, that is the default entry. So since there is a 1, there is a child with the label 1, then I go here and I remember P3 is so far the best match that has happened, and I go to the second bit and then say that is there a child with the label 1 to this corresponding node? Yes, there is. And then I come back and then remember P5 is the so far best match that I found out, and then I go and read the third bit of the destination IP address and again continue the search, and there is a node with the label 0, label 0, and I come back to I come to the node number P6. P6 is the prefix that is so far matched to the out, and then I go and read the fourth bit, which is a 1, but unfortunately I don't have a child node for P6. So for whatever is the best match that is found out is the P6. So what it means is, if your destination IP address is 11010 and if your set of prefixes are in this format, and the best match that you can find out is the P6, which is 110 star. So 111, the other ones P7 and P8 are not neither the P1 and P2 and P3. So this is the longest prefix that has matched for this particular IP address. So remember, P1 has also matched because default that is also matching. So using one, P3 is also matching, P5 is also matching, so is P6. But out of this, P6 is the one which is representing the longest prefix. So the routing decision need to be made by whatever the port number that is indicated against the P6 prefix. So here in this case, you need to forward it to port number 2. That is the meaning of so that is how the binary tries are constructed, and then the routing table. So you can think of this, if I have a data structure like this, and I am saying that the height of this tree or the trie is going to be 32. In the worst case, the number of the lookup operations that you need to do is 32. So this can be implemented using the linked list. So you just need to traverse this list up to one bit at a time. You read and then find out whether there is a left child you need to take or the right and you need to visit, and you keep visiting wherever you hit the dead end, and if that node is marked with the label some prefix, you actually could do the routing decision or the forwarding decision based on that particular node. So that's simple that. That's how the binary trie-based things are actually constructed. So now little bit look at if I want to build this trie, what all the components of what is there inside each of this node. So I can think of this, every node, a particular node inside this trie need to have three things. One is it need to have a pointer to the left child pointer, and the second thing it need to have is a pointer to the right child pointer, and the third thing that it need to have is it need to have a label or the port number on which the packet need to be forwarded. So you can visualize something like this. I have got two pointers, one is the left pointer, one is the right pointer, and this portion, upper portion, is actually telling me the port number on which the packet need to be forwarded, if it is a node with the particular label, not necessary that it should always have. So for example, any node which is not marked, here in this case this node is not marked and this node is not marked, and that node need not have this port number information. Only the nodes which are corresponding to or representing some prefixes, they will have this port number information. So P2 will have, you need to forward it to port number 1, P4 will have, you need to forward it to port number 4, something like this. And again it is obvious to see that if we have both the childs, you will have this left pointer set and right pointer set. If some node is having only one child, either the left or right, then it will have the other child set to the null. So that is how the XOR is going to work. So you either have you start with the root, keep searching, wherever you hit the boundary or the whatever the prefix that you have, there you stop it. So it might also happen that when you are doing the search, so for example, if my IP address is, let's say the destination IP address is 000, and so you start with the search, the first 0 you read, you come to the P2, and second 0 you read, come to the P4, and you read the third 0, you actually go to this node. But since this node is not marked, you do the routing decision based on the previous mask that you found out. Here in this case is the P4, meaning that using only the 00 star, you actually doing the routing decisions. That is the longest prefix that is matched for this IP address. So that is how actually this data structure works. So I repeat some of the formal concepts. The height of trie is 32, and the maximum number of comparisons in this case, here in this case, is the pointer traversal, left or the right. Pointer references is going to be 32. At every level you are going to have one, whereas either you decide to go to the right or to the left of them. And the node itself will have three components. One is the left pointer, right pointer, and the label or the output interface name. So that is how the I is actually constructed, and based on that the routing is done. So maybe let's take one more example of constructing the binary trie, and we'll right. So let's say the P1 is again star, P2. In this case, I'm going to ignore the interface number or the port number on which this one just the prefix notation. So this is 110 star, P3 is 111 star, and P4 is maybe 01 star, and P5 is 010 star. Construct a binary trie for the set of the prefixes. So as usual, I start with the root node, and then the P2 is saying that P1 is taken care now, is saying that 1 1 1 1, and then a 0 come to the left, and P3 is saying 4 times 1, this is the third one, and then the fourth one, and P5 is saying 0 followed by 1. So we haven't read the 0 so far, read that, and then followed by a 1, come to the right, and the P5 is saying 0 1 followed by a 0. So you go to this left, 0 followed by 1 followed by a 0, and the labeling would be something like this. So this is your default order P1, and P2 is 110. So that is the node here. This is your P2, and P3 is 4 times 1 1 1. This is the node which is corresponding to P3. P4 is saying 0 followed by 1, 0 followed by 1 is here. This is your prefix P4, and P5 is 0 1 followed by 0, which is here. So there are 5 prefixes, and there are 5 nodes with the corresponding label. Each one of them will have the references to the port number, so the other ones will not have, as I said. So as well, if you receive a prefix, IP packet with the destination IP address 11111 and 0. So this is actually 32 bits, but for the sake of convenience, I just written these 7 bits. So how do we do the thing? Read these 4 bits, and you will be in the P3, and that is the longest prefix that you can match. So based on whatever the P3 is saying, you need to route that particular packet to that particular interface. So that is how you implement. You take all the prefixes. So remember, prefixes are coming from the network component. How many bits are used for the works, and you take those prefixes and then construct a binary trie like this. And this is a software implementation. In the worst case, you need to do the 32 node traversals in this particular Okay. So this is one part of the implementation, but the question is it the best that we can do? So the answer is no. There are some improvements that we can make to this binary trie. We'll come back and see those optimizations in the next class. Thank you.